Okay, to make sure the simple dynamic system, okay, for this thing, that stored energy plus the power loss is equals to input. Okay, in this term, the purpose of this video is actually to strengthen this term and to actually strengthen how you actually would apply into different situations so that you can actually know how to apply into different situations so that it is much easier for you to analyze certain stuff. So what does I mean? How do I mean? What do I mean actually? So just to start off back here again, okay, if you remember, this is the internal energy, which is the amount of water, okay, from um maybe this is the amount of internal energy you have, and when you have a certain input, okay, an amount of water that is flushing in, eventually the change in the internal energy. So when the input comes in, okay, the input is, what do we call it? The u of t, right? So if we have a u of t that comes in, the input, you increase the amount of the water level from the initial state to a certain stage. There's a change. Okay, so this change is the amount of internal energy. This is the amount of change in stored energy that we have already made. And then once you input, okay, there will be certain losses. Maybe as I say, some random spots where actually some of the water may flow out. Okay, because um yeah, maybe there's some small holes over there. So when you input, and eventually some of the amount of the water will give rise to a change in the level of the water tank, while some of the input water will actually flow out. In this case, as a power loss. Okay, as a loss. So the loss is actually proportional to um whatever output it does. So the proportional wise, let's say this is 2/5 of the input, or maybe okay, hold on again. In ideal scenario, okay, input should be equals to output. Okay, for an ideal scenario, input should be equals to output. However, because we have a power loss, we assume that the power loss is proportional to the yt. Nonetheless, I will believe, okay, I may be wrong, I will believe that it is also proportional to the input itself. So therefore, 2 over 5 is maybe the power loss, while 3 over 5 will give rise to the water level. So you may wonder why actually I have repeat this thing again. Okay, because I actually didn't finish talking about what is. Previously, we were talking all about the inside of this physical system. We are trying to describe the physical system, right? This physical system over here, Nanda. And this physical system over here, the G of S, if you remember. But we didn't talk about the controller and such, because if you want to, try to control a certain physical system in the real world, you have to certainly make a controller such that the some sensor of the controller will actually sense okay, maybe if we reach certain level, okay, as we have all mentioned, that if we meet if the amount of our desired hold on again. So I draw this, I realized that so definitely okay, previously I was saying 2/5, okay, 2 over 5 is proportional to input also. That is partially correct. Okay, it may be wrong. That's why okay, for more strength, more stronger way in representing proportional to yt, okay, more stronger explanation, I would say that because we assume that yt is actually our height of the water at this point, okay, yt is our desired output. If the water reaches this water level, okay, this is our desired value. So this thing, the yt, that is the yt is actually the height of the water tank itself, right? So therefore it is so whatever power loss will eventually cause a change, will actually influence how the water level will increase, right? So if there is no power losses, okay, let's say we have no power losses, then definitely there will be an increase in the water level also. right? Due to that, whatever input is going into the output. You get what I mean? So this is a stronger explanation to explain why the losses is proportional to the YT. Because whatever losses will actually decrease the amount of um change in the amount of energy inside the tank. Okay, so it will actually affect the Y that we're talking about, the height of the water tank. Okay, in this case, okay. So it requires a lot of thinkings and such. So yeah, and nonetheless, as I say, what if we our water level reaches this point, and you don't want any more power losses to flow out. You just need to adequately because since there is also power losses over here, okay, these power losses compared to here is totally negligible. So therefore, you have a controller. Maybe controller would send there will be a control sensor over here. You'll feedback to whatever. So there will be a measurement as we measurement over here. So this measurement is actually this one. So it will measure the water level compared to something, and then you will feedback to your controller saying that if you reach this point, um, you you just send lower amount of water. That means at first maybe it send one maybe at first it may send 1 liter of water into the tank, but now since it reaches this brim, so in order to continue to let it continue to have this brim while the power loss is being um, so-called controlled, maybe we put in 0.2 liter so to prevent whatever losses over here that will decrease our height of the water level. I hope I get what you mean. I hope you get what I mean. Okay. So eventually, the controller itself is to control our physical system. So we are trying to build a system that could control any physical system. Okay, any physical system in the real world. And this is why all of the modeling and control theory all comes in. Okay, so physical system we have analyzed basically by the water tank analogy. But now, if you want to control, if you want to model certain stuff, you want to improve the efficiency. You don't want any losses that's coming from flowing out of the water tank if you are reaching the brim, or I mean if you reach the brim, okay, your desired value. So you don't want any more losses. So therefore, you want to decrease the amount of losses. And this is why we have a controller, and this controller will help us decrease our losses and eventually help us to solve our problem. So in order to sync this phenomenon, I mean this equation, this relationship between whatever input power will eventually give a change in the rise, I mean change in the water internal energy. Okay, so it gives a change in the internal energy of the system. So make sure it give a change. You're subject to a change. Okay, the height itself is the change in the internal energy. The internal energy at first is this height, right? But when input comes in, it gives a change in the overall height. Okay, in this case, the height measures the amount of water inside. So maybe to you to measure internal energy, maybe you need some energy sensor and then type of thing. So in this case, we use height to represent the amount of water inside the tank. This is why we use dy dt, but the y in this case is h. Okay, so therefore the input power will give rise to the amount of change in the in the stored energy, while you may also account for some power losses somewhere else. Okay, so I need to be very stressful that I need to stress that you have to understand that it gives a change. It doesn't you know it doesn't say that this is change in some other places or whatever, because when I study, I keep on trying to find out what is actually this. Okay, what is the true meaning of this? So I just realized it gives a change in the internal energy. So an example is let's say we have a heat flow into a thermal capacity. Okay, so we have an input heat flow over here we denote as Q, and then we have a so-called a power losses. Okay, K is some constant, while theta minus theta ambient is because when you input a certain um you know heat into this system, this is some materials, okay, this is some materials over here. So it heat up this amount of degree theta minus away whatever ambient. So apparently it will actually so-called whatever um hot energy will flow to the cold side, right? So therefore, if this is hotter than the surrounding temperature, eventually there will be a heat loss to the surrounding temperature. Therefore, there will be a heat losses over here. So as you can see, this equation is really something you need to need to really think a lot in order to derive this equation. It's not that simple to say because now I'm talking, so this is easy, but if you want to set up an equation like this, it's pretty hard for me. I don't know for you, but yeah, in the future or whatever. So this is considered a power loss, okay, because it's trying to give energy to the surrounding area. So it actually some loss, heat loss. While nonetheless, this amount of heat will give rise to a change in the temperature of the material, okay, governed by C constant, because if you remember MC delta T, okay, if you don't remember, never mind. So MC is just some thermal constant, but nonetheless, heat capacity actually. So yeah, so apparently it will give a change, okay. So let's say maybe perhaps at first it's maybe 30 degrees, so it give a change of maybe plus 5 degrees, while this power losses may be some 2 degrees. So 2 degrees losses may be due to the power, maybe due to it flows out. Okay, so the input is now itself can be due to the power, can be separated by power losses. So nonetheless, okay, anyway, so the amount whatever changes into the system plus whatever power loss give you whatever input that you have. Okay, this is what it means, which is also the water tank analogy. Okay, so this equation is very important, okay, to set up an equation. So eventually, all equations you have to set up in terms of this. So in order to control this, you have a not control, but rather than this is just some losses. So this loss is proportional to the amount of this. So this K is proportional to this thing, I would say, if I'm not wrong. Yeah, correct. Heat loss proportional to data minus. So hope I get this clear. So this is not a you can say that it's a feedback system, a closed loop, but rather than the amount of power losses. Yeah. So this one is for you to think. So I don't know how to explain. But nonetheless, you understand the meaning of the input power loss and stored energy, how it's being utilized in ways. So let me ask you this question. So what about this question? So which is input and which is output? You can see that control inflow, we have uncontrolled inflow, okay? There's water flowing in, there's water flowing in, and there is a water flowing out, okay? There you can assume that there's power loss. And therefore, what is it? So this is actually our power losses, or this is our input, okay? So actually this this equation, if you were to bring this power losses into here, okay, so it's plus. So this will be our change in the amount of internal energy we have, okay, height. So you may wonder, is this water tank analogy same as mine? Mine is a little different, okay, mine is uncontrolled flow out, okay. This one is a very controlled outflow, while there is uncontrolled inflow, which is a little different. But nonetheless, everything are the same analogy. And then just to let you know, if you set up the equation already, actually this is the volume, okay. So you have to set up in terms of some area and volume. So nonetheless, you reach this stage, you can just read the book, okay. And therefore, when you do some changes to it. Okay, maybe you have, okay, hold on. Maybe you need to bring this thing over here. Yeah. So if you bring this thing over here, meaning this will be plus, and this is kh. Kh is the power losses. Okay, if you remember, it's proportional to the change in the internal energy. So I assume that kh is the power losses, or this is the change in the internal energy, change in the stored energy, while this is the input. Okay, Fc. Assuming that they say that yeah, okay, anyway, assuming that there is no uncontrolled input to the system, so they assume that there is no uncontrolled inflow to the system, and this is why we cancel away Fu. Okay, not scolding you, but Fc. Anyway, so if you were to do that, you will get this thing over here. So this is the Laplace form, okay, and then if you were to bring this thing downwards, and if you were to bring this upwards, what do you get? You will have a transfer function. This is a transfer function g of s. Okay, output over the input. Okay, output over the input. So this is also rewritten as this. Okay, so this is the transfer function, and this is the input, or this is the output. Similarly, if you were to go back to this analogy, the same thing. You just, this portion is actually, okay. This portion is actually this one plus this one. Okay, maybe I should try to come back here. Okay, so if you were to look at this formula properly, so if you were to bring k multiply into these two terms, you'll get k theta minus k theta ambient, right? And then you bring this minus theta ambient over here. Wow, k theta, and you know this portion over here will be using Laplace transform, and you eventually get this one. And then this is the input plus the ambient temperature outside. Okay, and then you bring this downwards, and you bring this one is considered input because the environment, the temperature of the environment is also crucial to the, is also considered an input. So you just bring this over. So this is output divided by input if you bring this down, and then this 1 over cs plus k is actually our transfer function again. Okay, so I hope I have made this clear. Okay, if you don't understand anything, you just click back to the previous times and you just read it out. So I hope that I can make it clear that very importantly, this relationship is very important. Okay, it gives you that understanding of how stored energy is being changes from input, and how the power losses affects the internal energy, and then how controller is being implemented. Okay, how controller is being implemented, how, why closed loop system is so much important, and how k is also very important. The controller itself is very important. So therefore, in the next lesson 2, I will actually talk about um, what are the stuff that could actually make a system you know, stable. Okay, stable means that there will be no, okay, anyway, so we'll just, yeah, see you, bye bye.